the same in this process. Let's look at the anode. Over here at the anode, we've got zinc in the solid form, moving to zinc in the gas form. It's going to cost us, again, 130.5 kilojoules per mole. Once that thing's in the gas form, we got to ionize it. It's turned into zinc 2 plus ion. It's going to cost us energy. It's going to cost us 2,639 kilojoules per mole. Once we've got it in the ionic phase, it's going to go join that solution. That's an energy releasing process. It releases negative 2,247. So the total amount of heat change at the anode, you sum all these together, 522.5 kilojoules. And so actually the reaction that happens at the anode is a reaction that costs you energy. Let's look at what happens over here at the cathode. At the cathode, we've got this aqueous copper ion. Well, to get it to the solid phase, we first have to take it and move it into the gas phase. That costs us 2,289 kilojoules per mole. So it actually costs us money or energy to extract that aqueous phase copper ion and move it into the gas phase. Once we're in the gas phase, though, we throw 2 electrons on it. That's an energy releasing process. Remember, that releases 2,703.4 kilojoules per mole. So we're getting energy back. Now, once that thing has gotten its 2 electrons back, it's able to join the solid phase. So copper gas going to copper solid is an energy releasing process, and that's going to release 337.4 kilojoules per mole. You add all this together, you find out at the anode about negative 751 kilojoules per mole of enthalpy, or energy transfer as heat, is released over at the cathode. So at the end of the day, the net process is energy releasing. We take 522.5, subtract from it 751, we get somewhere around negative 229. I'll discuss that number in just a second. But take-home message is that the overall delta H for the reaction ends up being negative. That high negative delta H contributes to a negative delta G, right? We need a negative delta G for the reaction to be spontaneous, and that negative delta H contributes to that spontaneity. The negative delta H is the driving force to the spontaneity for that reaction.
When you give Cu 2 electrons, why is the releasing energy process on the second line?
Down here?
Yep.
Yeah, I put a negative here.
So why is it a releasing energy process?
Because you got a positive 2 plus nucleus, and you got a couple of negative electrons out there, right? Now, when positive charge and negative charge come together, energy is released, yeah. If you had those 2 negative charges stacked right on top of that copper nucleus, you would imagine the positive charges and negative charges exert attractive forces on each other. So if you want to separate them, you got to put energy in. You got to exert forces to separate them. Well, same thing. When positive charge and negative charge come together, energy is released. So that's why that guy's negative. At the end of the day, though, these steps take us from Cu2 plus zinc solid to Zn2 plus Cu solid. Now, we calculated negative 229.3 kilojoules per mole. In the calculation that we did up here at first, we calculated 218.66 kilojoules per mole. Because the 2 states, the initial state and the final state, are the same, those numbers should be exactly the same. There's a difference probably because the sources that I used for my tabulated values were different. And so there's a slight difference between those 2 numbers, but they should be the same for that delta H. When I give you problems in this class on exams, etc., I'm not going to have you breaking down each individual step of the reaction like we did just now for this, this copper zinc battery. Largely what you're going to be asked to do is take tabulated values of delta H not of formation and just look up the delta H's of the reactants and the delta H's of the products and execute a simple sum like we did here. Okay, so it's to the problems that you solve are going to be a couple steps. Look at the enthalpies of the products, enthalpies of the reactants, execute the summation report of value, tell me if it's endothermic or exothermic. I just wanted to break down that battery for you so that you can kind of get an idea of how these delta H's derive from electronic forces between particles. Okay? So, in this last reaction that we had a fairly complicated calculation. We had to look at the energies of the electrons bound to the atoms. We had to look at the energies of the atoms in the solid state bound to each other. We had to look at the energies of the ions in the aqueous phase bound to water. And once we considered all of those different energies, we were able to put together the delta H for the reaction. Something I'd like to note here is that this process is more complicated because you have atoms in condensed phases that are interacting with each other. When atoms and molecules in condensed phases, liquids and solids, are interacting with each other, each individual unit exerts forces on the other units, and all of those forces have to be incorporated into your calculation of delta H. Now, a simpler kind of system is gas phase species. So right now, we're going to look at a gas phase reaction. Oops. Before I do this, though, I'll use this as a chance to bend your brains. This reaction we're going to look at, we're going to take methanol. Methanol is CH3COH. We're going to combine this guy with O2 gas. It's going to be a combustion reaction. It's going to produce CO2 gas and H2O, or actually we'll do H2O gas. Stoichiometric coefficients become important when you're doing delta H calculations, and so the first step in any one of the any kind of this any of these kinds of problems is going to be to balance the reaction first. Anybody want to take a guess? If I've got 1 unit of H3COH, how many units of CO2 am I going to make? How many carbons here? 1. How many carbons here? 1. So what's the ratio of methanol to CO2? 1 to 1. So stick a 1 right here. Stick a 1 right there. All right? Now we're going to look at this and try to balance our hydrogens. We have a total of 4 hydrogens over here on the methanol molecule. The only thing that has hydrogens over here is water, and so we're going to have to provide enough waters to balance those 4 hydrogens. That isolates our coefficient from the water is 2 H2O. Now you need to balance your oxygens. You've got a net of 4 oxygens on this side, so you need a net of 4 oxygens over here. You've already got 1 oxygen present in that methanol molecule, so you're going to need 1.5 O2s to provide the other 3 oxygens that you need for balance. At this point, all of the atoms on the product side are balanced with all of the atoms on the reactant side. So hopefully we're getting good at this process back there. We look over here. This reaction is going on in the gas phase. In the gas phase, all of these species are separated from each other. And so you don't have, in the products, you don't have water molecules and CO2 molecules interacting. And so there's no energy that you have to calculate for bringing them into proximity together. And in the reactants, you don't have methanol and O2 necessarily exerting forces, so you don't have to worry about those. the things that change in moving from reactants to products in this reaction are largely the energies of the bonds. So if you can look at the total amount of energy stored in the bonds in the reactants and compare it to the energy stored in the bonds in the products, the difference is going to be the bulk of the delta H for this reaction. Again, this is because we don't have condensed phases and we're not worrying about the changes in energy when something becomes solvated by something else or when something joins a solid phase with something else. Largely, this is kind of like when we looked at the ionization potentials for zinc and copper. All we're really looking at with this is the bond potentials. To do the calculation for this, it's always sum of the heats of formation of the products minus sum of the heats of formation of the reactants. You can look up in a standard table, and you can find out the heat of formation for CO2 was negative 393.51 kilojoules per mole. You have one CO2 in your product, so we'll put a coefficient of 1 here, multiplied by that. We've got 2 waters in our products. The heat of formation of water is negative 241.82 kilojoules per mole. So we'll multiply that by the coefficient of 2. So now we have the sum of the products. We're going to subtract from that the sum of the enthalpies of the reactants. We've got 1 methanol, so we've got a coefficient of 1. Multiply that by the heat of formation of methanol, negative 200.66 kilojoules per mole. We've got 1.5 O2s. You look up in the standard table for the heat of formation of O2, it's 0, because that's the reference state. We'll talk about what that means later. Products minus reactants for this reaction then is 676.49 kilojoules per mole. What that means is that when you move from products to reactants, when you take 1 mole of methanol and you combine it with 1.5 moles of O2 to produce 2 moles of water and 1 mole of carbon dioxide, negative 646.49 kilojoules of energy are released as heat. Okay? That's the value that we got from looking at the heats of formation of the products and the reactants. Now we're going to go about calculating this number in a slightly different way for illustrative purposes. If you go consult a text, you can find tables that list the average bond energies for different kinds of bonds spread across molecules. Because we're in the gas phase, and largely the things that have energy, the potential energies, are only the bonds, we can approximate delta H for this reaction by simply asking the question, how much energy did we have to spend to break the bonds in the reactants, and how much energy was released when we formed the bonds in the products? We're going to do this calculation in our reactants. We've got methanol, which has 3 carbon-hydrogen bonds, 1 carbon-oxygen bond, and 1 OH bond. We have O2, which has 1 oxygen-oxygen bond. So 3 carbon-hydrogen bonds, 1 carbon-oxygen bond, 1 OH bond, and 1.5 O2 bonds. Average bond energy for a carbon-hydrogen bond, averaged across many different molecules, is about 413 kilojoules per mole. It means to break a carbon-hydrogen bond, you got to put 413 kilojoules of energy. Average energy for a carbon-oxygen bond, 358 kilojoules per mole. You got to put 358 kilojoules in there to break a carbon-oxygen bond. OH bond, 463 kilojoules per mole. O2 bond, 495 kilojoules per mole. We're going to break all of these bonds to form the new bonds. So 3 times 413, 1 times 358, 1 times 463, 1.5 times 495 is 2,802.5 kilojoules per mole. So we've got to put in 2,802.5 kilojoules to break all of those bonds in our reactants. that's we put a positive sign on that energy because that's energy we have to deliver to the system. Now, once all of those bonds are broken, we can form all of the new bonds. In terms of the new bonds, we're going to have, in this carbon dioxide molecule, the CO2, we're going to have 2 carbon double bond oxygen bonds. And we're going to have 4 OH bonds in the water. So we're going to put a negative sign here because when these bonds form, it's energy released. Negative 2 times 743, negative 4 times 463. Add those together, negative 3,338 kilojoules per mole. So just accounting for the bond energies, the average bond energies, not the real bond energies, but doing this approximation using average bond energies, we get that the delta H is approximately 535 kilojoules per mole, negative 535. So we had a positive value, and we had a larger negative value for a net negative delta H for the reaction. 535 kilojoules per mole. Now note that when we calculated up there using the heats of formation of the actual species, we calculated negative 676 kilojoules per mole. So there's a difference there. The difference exists because, again, this is an approximation. When we did this bond energy calculation, we used average bond energies. Those average bond energies are not necessarily the same exact bond energies that we'll have for those bonds in our particular reactants and products, but they're similar. And so the whole point I'm trying to make is that if you're only looking at changes in actual bonds as you move from products to reactants, all you're dealing with is one type of bond versus another, then largely you can approximate delta H just by seeing how much energy is stored in bonds in reactants versus how much energy is stored in bonds in the products. And the difference will give you your delta H. Just for some practice, I wanted to remind you that every problem can be looked at as a redox problem. If we take this guy and we look at redox numbers, remember you don't need stoichiometric coefficients when you're looking at redox numbers. Demonstrate these calculations real quick here. For the methanol molecule, we had a demand for 2 electrons. We had 1 oxygen at 2 minus oxidation, right? So we have demand on some level for 2 electrons. We've got 4 hydrogens around that are the least electronegative. That oxygen is going to put at least 2 of those hydrogens at +1 state. You can think of it as putting 2 of those hydrogens at +1 when it steals those electrons. What we've got left then are 2 hydrogens and 1 carbon. Well, the carbon's more electronegative than the hydrogen, so the carbon's going to go to a 2 minus state when it puts those other 2, the carbon goes to 2 minus when it puts the other 2 hydrogens at 1 plus. So oxidation numbers for these guys, all the hydrogens in this molecule are at 1 plus. Your carbon is at 2 minus, your oxygen is at 2 minus. I want to remind you that when you do these oxidation number calculations, the sum of the oxidation numbers should equal the charge on the species. In this case, all of our species are neutrally charged. You'll see that 3 times +1 for these 3 hydrogens, 1 times -2 for the carbon, 1 times -2 for the oxygen, and 1 times +1 for that hydrogen, all sum to 0. So oxidation number should sum to the charge on the species. Same thing over here. We've got for your CO2, or for O2, all the species are oxidation number 0. I'm not going to show that calculation. But for CO2, you've got 2 oxygens at -2. So you've got a demand for 4 minus. The only player for that to come from is the carbon, so that carbon is at 4 plus. Note that the sum of the oxidation numbers on the oxygens plus the carbon is 0, which is also the charge on the species. Your water over here, you got 1 oxygen at 2 minus. That's going to put both of those hydrogens at a 1 plus state. 2 times 1 plus for the hydrogen plus 1 times -2 for the oxygen is 0. Again, that is the net charge on the water molecule. If you look going from products to reactants on this, your carbon in the reactant starts off at 2 minus, and the products it ends up at 4 plus. Your oxygen in the reactant starts off at 0, in the products it's at 2 minus. So carbon loses electrons, it's reducing oxygen, therefore it's the reducing agent. Your oxygen gains electrons, so it's oxidizing the carbon. You would say that electrons flow from the carbon to the oxygen in this reaction. Carbon's oxidized, oxygen is reduced. So that's just some practice with oxidation numbers. We're going to talk more about enthalpy, and I'm going to have a lot of problems for you guys to practice on Thursday and next Tuesday. But I guess the take-home message from today's lecture is that enthalpy is energy exchanged as heat in a process. And largely, you can look at all of the binding energies present, or all of the binding properties that change moving from reactants to products. And if you can sum all of those enthalpies together, you'll get the overall change in the enthalpy for the process. Did that make sense? We good for a minute? What time is it? 9:53. We've still got 7 minutes. All right, let's look at one more thing. One more example. So we looked at the gas phase reactions. We looked at the batteries where we had solid and aqueous states that we had to consider as well. One more place that you're going to see this is when we look at the heats of solution for salts. So we've discussed this a million times, but when you've got a solid salt, you've got some kind of a regular three-dimensional arrangement of positive charge and negative charge that are stacked right on top of each other in rigid positions. Yeah? So that's our solid. When a solid dissolves, if a solid dissolves, the positive ions get solvated by the negative water dipoles. I've resorted to drawing waters just as little v's, and so you have to note that that was the shorthand that I used up here in this. What that V indicates is that your O's at the point is here and the H's are there. So the point of the V is the negatively charged oxygen atom, and the two legs of the V are the positively charged hydrogens. So your positive charges get surrounded by waters like that, and your negative charges get surrounded by waters like this. Your delta H for these solubilization processes is the difference in the binding energy in the solid versus the binding energy for the solvated ion. If you've got stronger forces in the solid than in the aqueous solvated stage, then you go up in energy to go to the aqueous phase. And so that would be an endothermic process going towards the dissolved product. If you have weaker forces in the solid phase than in the solvated phase, then you would go down in energy going from the solid to the solution. And so you're going to be given calculations that you'll have to do where you have the products and the reactants. The products will either be the solid or the solvated stage, and the reactants will be the solvated or the solid stage. The differences in the energy and the delta H that you calculate for those using tabulated values is the difference between those binding energies in a solid and a solution. All right, I'm done talking. Somebody else can talk to me if you want, but I'm not going to say anything else unless I'm prompted. Questions? Was that heavy? Sorry, I know it was dense, but the theory is that now you've got all the tools in your tool belt, and now it's time for you to go to work doing homework, and hopefully that means that what we do on Thursday and Tuesday next week is just practice from the exam. All right, see you in lab.